So hello everyone, welcome to electromagnetic waves class. So in the last session we have seen some couple of examples. So based on that, now in this session we are going to see what is electric field intensity due to a conducting sphere. So our today's topic is electric field intensity due to conducting sphere. So so let us have a one conducting sphere with us, and this conducting sphere has radius r, and we will be depositing charge q on that conducting sphere. So I'm assuming a conducting sphere here. So so and what I'm doing here is I'm depositing positive charge here. So this is the positive charge here which I'm going to deposit in this conductive sphere, and its radius I'm denoting it by r. So radius of this conducting sphere is denoted by r, and and plus q charge I have deposited here. So this is basically a hollow conducting sphere. So let us I'll write here. So this is a hollow conducting sphere. So the charge is distributed over this as a surface charge density. So whatever charge it is there, so this is distributed as a surface charge density. So this is surface charge density, and for this we have to consider three cases. So now here we have to calculate the electric field on this conducting sphere. So what I'm going to do is I am taking as a three, I'm considering three cases here. So let us consider three cases. So let us consider here three cases. So first case will be when r greater than. So that will be our first case. Second case will be when r will be equal to r. Third case will be when r will be less than or equal to r. So that will be basically on the surface. So let us remove this. So I'm going to remove this. So this will be only less than r, and this will be inside the surface. This will be inside the surface. So let us consider the first case. So our first case will be, let us consider the first case. So our first case will be when r is greater than r. So in this, so I'm assuming two connecting surface here, and the small r should be greater than r. So let me make this figure here in a clear way. So then things will be more clear to you. So let me write it here. So suppose this is our one surface, and this is our which I'm denoting it by plus r. So this is our plus r, and this is our plus r, and this in the smaller we are putting some small r here, and this is our greater circle. So and this length is denoted by ds, and this is denoted by ds. And so as per Gaussian law, so as per, we are already aware of the Gauss law. So what I will write here, so as per Gauss law, so electric flux will be equal to rho into E, integration of rho into E. So we are already knowing the Gaussian law. So based on the Gaussian law, I have written this electric flux. So if I consider a small surface over here, the direction of the surface will be with respect to center. So whatever the direction will be there, that will be with respect to center only. So we will be in the same direction. So electric field and surface will be parallel to each other. So if you can see this line and this line, both line are parallel to each other. So is my screen is visible to you? So as you can see in the figure, these two lines are parallel to each other. So in this case, what I will write, the electric field is parallel to ds. So that is our Gaussian surface. So in the first case, what I will consider, that theta will be equal to 0. So as we are already knowing, the value of ds will be 4 pi into r square. So that will be, so what is this? This is basically the surface area. So basically this is the surface area. So what I will write here, theta by epsilon naught. So this is our first case. So what will be our electric field here? So the electric field which we are getting here is E is equal to 1 by 4 pi epsilon naught into q by r square. So if in the first case, so as per the Gaussian law, what I've applied, so I was getting that electric field is equal to phi into E. So that the electric field will be parallel to the ds vector. So and the ds which I'm denoting is it as a surface area. So for in this first case, theta will be always equal to 0. So E into 4 pi r square equal to theta by epsilon naught. So therefore electric field will be E equal to 1 by 4 pi epsilon naught into theta by r square. So what I can write here, that direction will be in the direction of r vector. So I have to denote this r vector here. So both direction will be same. So let us consider, so this is all about the first case, which where I am calculating the electric field intensity due to the conducting surface. So what I'm getting here is that the electric field will be equal to 1 by 4 pi epsilon naught into q by r square. So q will be the charge which I'm depositing into the surface, r will be the distance from the surface, and that will be the r vector which I'm denoting here. So this is our first case. So I think the first case is clear to you. So, so let me tell. So please tell me if any doubt is there regarding this first case. So what I've told you, is this clear to you? So are you getting my point? What I'm trying to say here? Yeah. Okay. Fine. So let's move to the second case. So how how we are calculating the second case? So I've already told you that we will be considering three cases. So first case will be when r is when the smaller radius will be less than r. When the second case will be the both on the surface, that will be r equal to r, and third surface will be outside the surface when r will be greater than r. So the small r which I'm representing it is by for the smaller circle, and the bigger r will showing you the larger circle. So let us consider the second case. So let us consider the second case. So when r is equal to r. So this is our second case. So what I will do here. So first of all, I will apply the Gaussian law. So I will write here, after applying after applying Gauss law, what I will get here. So that will be E dot ds is equal to q by epsilon naught. So we are already aware of this term. So when we will apply the Gauss law, so this value is I'm getting. So what is this? This is our surface area. So ds will be representing the surface area. So here also surface area is parallel to electric field. So what I will write here, so electric field is parallel to ds. So both are parallel to each other. So E is parallel to ds. So let me calculate this. So E will be parallel to surface area. So in this case, the value of theta will become 0. So when I'm considering this, that E will be parallel to ds, the value of theta is almost getting to 0. So what I will write here, so E into 4 pi r square equal to q by epsilon naught. So I will calculate the value of E equal to 1 by 4 pi epsilon naught into q by r square. So this is the value I'm getting for the second part. So when you substitute the value of, so when the value of E, so that value you are going to get when you are substituting the value of E in the both the equations. So I have derived all those two terms which is there. So before moving to another term, let me discuss some of the terms which are related, which are coming into your paper. So first of all, what they're going to ask you is, so first of all, they are going to ask you what is capacitor. So basically, if in one line, if you are going to decide what is capacitor, so that will be very difficult for you. So and they are asking in the most of the papers. So if so basically, if I have to so if anybody has any idea how to define capacitor in a simplest word, so how you can define capacitor in one line. So what does basically capacitor do? So if you have any idea, you can tell me. So yeah. So basically, what does capacitor do? So what is the working of capacitor? How is it helpful? And what are the things capacitor are capable of doing? And why it is very important in as electronic point of view? So if anybody has any kind of idea, they can tell me. So let me remove this. So I'm removing this. So the heading I'm putting here is capacitor. So what is capacitor? So basically capacitor is a passive two-terminal electric component and which is used to store energy. So if in one line definition, if somebody is asking you to how to define capacitor, so basically capacitors are used to store energy and electrostatically in an electric field. So if I'll write a definition of capacitor here, so what I will write here, definition of capacitor. So basically a capacitor is a passive two-terminal electric component which is used to store energy. So basically which will store energy electrostatically in an electric field. So the main work of the capacitor is used to store the energy in the electric field. So basically there are two types of capacitors are there. So I will tell you, the first one is the parallel plate capacitor. So how you are going to define the parallel plate capacitor? So basically, so here dealing with the capacitor with the two parallel plates. So let us suppose this as a, so I'm denoting the figure of the parallel plate. So suppose I'm taking this as one plate like this and other plate like this, and here this is y vector, so this is x vector. So this is basically at z is equal to some d and this is z is equal to 0. I'm imposing some positive current here, doping with some positive current here, and I'm imposing some negative current here. So and this is rho s. So basically this is the Gaussian surface charge. You can tell it like surface charge. So this is our surface charge. This is our surface charge. This is our surface charge. So this surface charge I am denoting it by rho s. So rho s, this is our surface charge. So if I'll write, so let me remove this. So let me remove this. So let me remove this. So what I'm denoting, so what I'm imposing here, that positive charge I'm imposing at the positive charge on upper plate and negative charge on lower plate. So two type of charges I'm depositing on this capacitor. So two parallel plate capacitor I'm putting here at z equal to 0 and at z equal to d, and I am superimposing positive charge on the upper plate and negative charge on the lower plate. So what is, so and surface charge density which I'm denoting it by surface charge density which I'm denoting it by rho s. So rho s is my surface charge density. So what will be the capacitance here? So let me calculate the capacitance. I'm taking a class, I will call you in some time. Taking a class, I will call you in some time. So surface charge density, so what the capacitance will be? Capacitance will be C will be equal to Q by V. So this is our equation number A, and So this is our capacitance. So we have already derived this value of capacitance. So the capacitance which I am representing it by C, Q is the positive charge here, Q is the charge here, V is the distance. So and so for calculation of charge, so how to calculate the charge from this? So how we will calculate the charge? So for calculation of charge, what I'm going to do for calculation of charge, so Q will be equal to rho S into area. This will be our equation 1. So this is our surface charge and this will be our area. So I've already told you that the V vector which I'm showing you, that is for area. So now how to calculate the voltage potential difference? So for voltage, I've already told you how to calculate the voltage. For voltage, V will be always equal to minus E dot dl. So first of all, we need to understand the direction of electric field. So where the electric field will be moving, so from that we will calculate the voltage. So voltage will be E dot dl. So dl will be the line charge vector. So and direction of the electric field. So actually the charge is moving from positive to, so the direction will be this will be this direction. The direction of the positive charge will be, so I will denote it with other color. So this will be the direction for this. So this will be the direction for positive charge which is imposed. Direction for negative charge will be towards itself. So direction for the negative charge, I am denoting it here. So as you can see in the figure, it is already if it is visible to you. So this is the direction of the two superimposed positive charge and negative charge. So now what I am going to calculate the total electric field. So the total electric field will be equal to E equal to E1 plus E2. So this will be our total electric field, that is E is equal to E1 plus E2. So for E1 vector, what I have calculated here, that will be rho S upon, so see, this charge is moving from positive to negative. So the direction I have taken like this. So this is moving from positive to negative. So for E1 vector, what I'm writing here, so for E1 vector, rho by 2 epsilon naught into minus a cap z, because since it is moving away, so I have substituted the value minus here. Since the charge is moving away, as you can see in the figure, it is moving away from the positive charge. And for E2 charge, what I'm going to do, for E2 charge, I'll write here rho s upon 2 epsilon naught into a cap z. So a cap z. So this is for this E2 vector. So, and if I'll take the summation for those, I'll calculate here minus rho s by, if I'll take minus outside, minus rho s by 2 epsilon naught into a cap z. So this will be our total electric field which we are getting. So I think this is clear to you. Is there any doubt how I have calculated the electric field? So first of all, I have calculated the charge. After that, I have calculated the potential difference. The V. What is V denoting here? Actually, V is potential difference here. And after calculating V, I had applied the total the formula that the total electric field will be equal to the electric field of first plate capacitor plus the electric field of second plate capacitor. So whatever value I am getting here, I have just substituted the value here, and based on that, I have calculated the total electric field. So let me write in a clear way, then things will be more clear to you. So let me write in a clear way. So are you getting it? Is there any doubt? Okay, fine. So okay, so let me write here. So what is the value? So the value of E which I am getting here is E is equal to minus rho s by epsilon naught into a cap z. This is the value of E. So this the value of E which I have calculated based on the electric field of the electric field of the first plate, and since it is a parallel plate capacitor, so it will be having more than one plate. So based on that, I have calculated the electric field of this capacitor. So now in the next what I'm going to do, so now I'm going to calculate the potential. So after calculating the electric field, I will calculate the potential, and let me substitute the value of potential here. So what I will write, so potential, as we are already aware that potential we are denoting it by V. So V will be equal to minus, limit will be 0 to D, since because the upper plate capacitor I have put it here Z equal to D, and the lower plate capacitor I have put it here Z equal to 0. So it is varying from 0 to d. So that is why I have put it, I have substituted the limit here 0 to d, and the value of electric field I'm getting here is minus rho s by epsilon naught into dz. So basically dl will be varying from minus 0 to 0 to d. So I'll write here in bracket. So dl is varying from 0 to d, and this a dz will be varying will be the whole capacitor plate. So dz will be the whole capacitor plate. So based on that, I have written the formula for the electric potential, how to calculate the electric potential. So if you will open this limit, so what you are going to get, so that will be rho s by epsilon naught into z, and limit will be from 0 to d. So when you will open this integration, what you are going to get, you will get here rho s by rho s into d upon epsilon naught. This will be our second equation. So we have calculated the electric field here. We have calculated the electric potential here. So now what I'm going to do, so now I am putting the 1 and 2 in equation number A, so which I have denoted earlier. So as you have already seen there, so one equation I have denoted by A. So now so the first equation will be the electric field equation. Second equation will be the the potential equation, that will be V equation. So these two equation will be there. Now these two equation I'm going to substitute in the equation A. So what I will write here, put 1 and 2 in the equation A. So equation A, which we have seen already. So now these two equation I'm going to substitute. So now what I will get here, so already we are aware that C is equal to Q by V, and Q, the value of Q will be rho s into area upon rho s into d by epsilon naught, and based on that I'm going to calculate epsilon naught into epsilon r into a by d. So this value I'm going to calculate. So in general, epsilon naught will be there, and since it is a dielectric material, we have to place epsilon naught r. So if in the paper they are asking you to calculate the electric field due to the dielectric material, so for that you need to multiply epsilon naught r. So for that you have to take one more term, that is epsilon naught r, and you needed to multiply it into epsilon naught. So I can write here. So if somebody is going to ask you what is the generalized formula for the parallel plate capacitor, how to calculate a parallel plate capacitor in a dielectric medium. So if they are going to ask you this question, so this formula will be there for a calculation of a parallel plate capacitor. So I'll write here, for calculation of parallel plate capacitor, that will be equal to epsilon naught into epsilon r into a by d. And if they will be asking in the simple medium, you just needed to write here like epsilon naught into a by d. If they are asking you to calculate in a dielectric medium, you needed to multiply it by epsilon naught r value, and that value will be given in the paper. So what you have to do, you just needed to multiply all those values. You will get the how to calculate the electric field due to a parallel plate capacitor in a dielectric medium. So actually this formula is very important. A couple of questions are there in your RTO paper also, in GATE paper also. So based on that, we will see some numerical also. So I think this is clear to you. Is there any doubt based on this, how to calculate the electric field and due to a parallel plate capacitor and all? Is there any kind of doubt? Are you facing any kind of difficulty? Okay. So no doubt. So this is clear to you. So we will solve some problem, how to calculate the values. So based on that, we're going to solve some problem here. So I have already told you the syllabus for the midterm 2. I have discussed you with the syllabus of the midterm 2, what are the topics we have covered and what are the topics which are going to come in, which are going to be asked in midterm 2 for electromagnetic waves. So, and biomedical also. So try to go through that topics, and one numerical will be there, and two to three theoretical question will be there. So try to solve those paper, and solve those numericals also. So anything will be asked. So now see, as per the Gauss law, how the charges are moving in those parallel plate capacitor. So, and one more thing I have forgot. So that for the third case that we have lost it. So how to calculate the third electric field intensity for the third case, that will be R less than R. For this I have forgotten. So I will show you how we are going to calculate. So this is our first, this is our second plate, and this is separated by distance R. This is R, second R, and in this case smaller r is less than r. So over here, if you apply Gauss law, then there is no charge which is enclosed by the radius r. So no charge which will be there which is enclosed. So what I will write here, E dot ds equal to q by epsilon naught equal to 0. So why I have written 0 here? Because there will be no charge which is enclosed here. So because of that, we are getting the value as a 0. So no charge value will be there. So I'm getting here 0. So what I will write after substituting, what I will get here, value of E will be equal to 0. So inside the surface electric field will be 0. So let me make the graphical representation for this. So how we will deal with graphically with this. So this is distance. So first the electric field is constant in this term. So in this part the electric field is constant, and now in this part the electric field is lagging here. And so what I will write here, E is 1 by r square, that is r greater than r. So what I will write, E is equal to r, that is E equal to 1 by 4 pi epsilon naught into q by r square, that is highest electric field. So this will be r greater than r. So this will be r. So as you can say, so this is what the electric field is varying in those field. So the example which I have covered you. So I have asked one question. So in this question, they were asking you to calculate the electric field intensity. So I have told you how to calculate those electric field intensities. So let me tell it how to calculate this electric field. So they are asking you to calculate the electric flux. So the formula for the electric flux is given as, so what is the formula for electric flux? Flux equal to q by epsilon naught, that is 4.02 into 10 to the power minus 5 upon 8.85 into 10 to the power minus 12. So this is the charge which is given as, and surface area is given as, so what I will write here, electric flux will be equal to 4.454 into 10 to the power minus. So if you will substitute this value in calculator, you will get a clear idea. So what I am getting here, into 10 to the power 6 microcoulomb per C. So this was a numerical which I have given you how to solve it. So you just needed to substitute the values of the electric the charges here and the value of flux here. So by this you can substitute it, and after this you can get it. So second numerical which I have given you, so for that I had asked you to calculate the density which is equal to Q by A. So basically it is Q will be denoted as charge and A will be the area. So what I will write here, that Q will be equal to D into A. They are asking you to calculate the value of Q. So what I can write here, Q will be equal to D into 4 pi R square. So for that, Q will be equal to 20 into 10 to the power minus 6 into 4 pi into 0.42 meter square by meter square. So this two will get cancelled, and we will get the value of Q, that will be equal to 4.02 into 10 to the power minus 5 C. So this is all about the numerical which we have seen. So I think this is clear to you, and by this we have completed our topic which is coming to the midterm. So if you are having any kind of doubt, if you are facing any kind of difficulties in those topics, kindly consult with me, because you can write me, you can call me or anything. So this is the syllabus for the second midterm which I am covering now. So I think we have seen how to calculate electric field to a parallel plate capacitor, how to calculate electric field for a Gaussian surface, and how to solve a couple of numericals there based on those electric field. So I think things are clear to you. Is there any doubt? Are you facing any kind of difficulties? So am I clear to you all? Okay. So how I have calculated the D? So actually I have substituted the value of that charge, and I have substituted the value of area here. So whatever the value of charge I'm getting, whatever the area I'm getting, I have just substituted in the formula, and based on that I have calculated the value of charge here. So nothing new here, no rocket science is involved here. So altogether you have to do is you have to just read all those formula which I've given you, and based on that you have to solve the topics. So this is all for today. Uh, and we will try to meet in the coming days, and prepare your midterms syllabus in a good way that you can cover all the questions which are given in the paper. So thank you very much for the today session. We will meet in the coming days. Thank you. मैडम मरवाएंगे कहाँ हमको? ये ग्रुप पे ये उस पे वीडियो जाता है।